what kinds of languages can be accepted by stack machines? You know, we've talked about several categories of languages already. We had the regular languages. Those are the languages of NFAs and DFAs. We had the context-free languages. Those are the languages which are generated by context-free grammars. And we already saw that every regular language is a context-free. What about the stack machine languages? Are they related to regular languages? Are they related to context-free languages? We've already seen that you can do, for instance, A to the n, B to the n. You can do that on a stack machine. That is not a regular language. It turns out, actually, and this is what I wanted to finish talking about today, you can do any regular language on a stack machine. Let's talk about that. Any regular language. On a stack machine. It is possible. Put an extra H in there. Machine. I can do that on machine. Any regular language on a stack machine. Actually, this is something that I mentioned last time. I don't know if you really noticed it, but we had an example of a stack machine that was the same as an NFA. And if you have any regular language, of course, you can make an NFA out of it. And then there's a standard procedure to translate that into a stack machine. Let's see how we do it. So I'm going to just do an example here. What about this NFA? Oh, I got these squeaks. This marker was like the best marker last time. What happened to you, marker? I gotta shake it, I guess. So we got an NFA here. A here, B here, A here. All right, this is an NFA. I don't care really what the language is. Let's say this is an accepting state. Like I said, there's always a standard procedure for turning an NFA into a stack machine. It involves you think of the states as stack letters, and every time you do a transition on the original NFA, it corresponds to changing the stack from an S. For instance, this transition here, you begin with the stack saying just S on it, and when you follow this arrow, you pop that S and you replace it with a T, and that's all you do. So the stack always has a single character on it, and you continually pop that character off and push back on the new character. So a diagram like this will translate directly into a stack machine. Read, pop, push, all right? And like I said here, this S to T arrow looks like read A, pop S, push T. So this, I mean, it's easy enough to just memorize this procedure, I suppose. But you think of these states are going to be sitting on the stack. Only one of them, such a stack machine that I'm going to write here, will never end up putting more than one thing on the stack. So the stack always just stores in it the state that the computation is in. All right, so that's one. And then just every one of these arrows translates directly into an instruction for the stack machine. So we're also going to do read A, pop S, push Q. That's this arrow here. All right, this B in the diagonal here is read B, pop T, push Q. This A going up here is read A, pop R, push T. And then this epsilon here is read epsilon, pop Q, push R. All right, and this is basically it. There's one more thing that we need over here. There's one aspect of this stack machine which I have not expressed yet, and that is the fact that R is an accepting state. And the way that you indicate, so these, just for your notes here, I'm going to say these ones here refer to the NFA transitions. And the one final line here, and I suppose you have to just remember that this is what you want to do. This indicates that R is accepting. So for any accepting state, you put lines like that, epsilon R epsilon. If T was accepting, I would also put epsilon T epsilon, but T is not accepting, so I don't put that. All right, epsilon R epsilon. This allows you to finish the stack derivation at the very end in the final step. All right, If you can remember this basic procedure, you can always easily translate any NFA into a stack machine. Let's see, just to demonstrate that this is actually correct. How about, can we see what is accepted here? How about AB is actually accepted on the original machine, because I can do A followed by B followed by epsilon, right? AB is accepted. Can we demonstrate that by using the stack rules? Unfortunately, I'm out of room, so I'm going to erase the NFA, because actually, before we do that, you want to have this picture in your mind. I'm going to erase it. Don't you erase it. I know you never erase anything. I know you. All right, so I said what we're going to do, AB is accepted. I hope you didn't erase that NFA. Let's try to prove that on the stack machine, right? Can we show that actually AB is accepted using these stack rules? I'm going to go AB, comma, S, and I have to do this arrow thing over and over again, eventually ending up with epsilon, comma, epsilon. What is my strategy? There's so many rules here. In fact, there's already 2 different rules I could do when I read A and pop S. Which one should I do? Cast your mind back to what the NFA looks like. I hope you still have that on your paper. You didn't erase it. Look on the NFA and think about which arrow would you follow, and then do that rule on the list here. So what you should do on the NFA, if you want AB to be accepted, on that picture you got to go across and then diagonal, I don't remember the letters, over to T, down to Q, and then do the epsilon transition over to the R, all right? So those are exactly what I'm going to try and do. First, I'm going to do this first one here, which was the arrow from S to T. So I'm going to read A, pop S, push T. It now looks like B, comma, T, right? Next, I'm going to go that diagonal arrow on the diagram, which was read B, pop T, push Q. So this now, I read the B and it becomes epsilon in the front, pop T, push Q. So now it's epsilon, comma, Q, right? And then finally, you do the epsilon transition over to the R. That would be this last line here, not last, second to last here. Read epsilon, pop Q, push R. So it's epsilon, comma, R. That's an epsilon right there. All right, and then finally, R is an accepting state. To actually finish on the stack machine, you do this rule. That's why this is necessary, this last special rule to indicate the accepting state. Epsilon, read epsilon, pop R, push epsilon. The only effect of that is just to kill this R and make it an epsilon. And that is epsilon, comma, epsilon means it is accepted. Come on now. Just trying to write a satisfying check. I'm so satisfied. All right. AB is accepted. Great. So this is how you take an NFA and turn it into a stack machine. Can I just say one last thing? That's basically all I wanted to say. One last thing. In terms of, I said, the larger question, what kinds of languages are accepted by stack machines? If you believe that that procedure that we just talked about is always possible to do, that means any regular language can be the language of a stack machine, right? Because any regular language has an NFA, and any NFA can automatically be translated into a stack machine. So here's a theorem. I'll write it as a theorem. If L is a regular language, you know what I'm going to say here, then L is the language of some stack machine. Then L is the language of some stack machine. It really is. All right, that means the languages that you can do on a stack machine, they automatically include all regular languages. All right, we just talked about converting NFA to a stack machine. It's a natural thing to wonder, could I do it for any grammar? It turns out the answer to that is no, you can't convert any grammar to a stack machine. But there is a procedure to convert any context-free grammar to a stack machine. So that's what I want to talk about next. Context-free grammar to a stack machine. It turns out you can convert any context-free grammar into a stack machine, and actually you can go the other way too. Let's start with this way. If you have a grammar, can you make it into a machine? Let's just to refresh our memory on working with grammars. Here is an example. How about S goes to A, B, S, A, or T. T goes to B, T, or epsilon. So this is our grammar. Just for fun, let's make a derivation of a string in the grammar. How about A, B, A, B, 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 A, A? Just so we are all clear on grammars, I want to derive this word using the or this string using the rules from the grammar, and probably this is going to work out if you just think about what you want to see at the beginning. S goes to, I think I should do this once, right? S goes to A, B, S, A. So here's a derivation of that string over there. S goes to, sorry, it's the wrong arrow. We've got several kinds of arrows. It's not a big deal. I might as well do it right though. In the grammar derivation, you do that one. S goes to A, B, S, A. That's because I want an A, B on the front. And then I want another A, B. I guess I'll do that one again. So now I go A, B, S, A, right? This S became another A, B, S, A. Okay, so now I have A, B. That's good. Next, I want to see 3 more B's and then 2 A's at the end. I have the 2 A's at the end, so I want to see a bunch of B's. I should make this a T. So A, B, T, A, and then this T to B, T, I can do that 3 times to make some more B's in there. So A, B, B, T, A. There, I just did that one once. I'm going to do it again. A, B, B, T, A. All right, and then do one more time. A, B, B, T, A. All right, show your parents this video. This is what they're paying for. And then finally, so this is the string here. I don't want the T in there. I go T goes to epsilon, and that's the end of the story, right? A, B, epsilon. I'm just not going to write it. A. And there is my string. That's the derivation. All right. The reason I wanted to get this down on paper is because when you convert to a stack machine, you want to think of this derivation sort of in the back of your mind as you are doing your stack machine computation. Anyway, I will tell you, how do you translate the grammar to a stack machine? It's a very simple procedure, which seems mysterious at first, so I'm just going to tell you how to do it first, and then we'll talk about why this works. Let's do it. All right, let's write our rules for the stack machine. So first of all, as sort of a preliminary, what is the alphabets that we're going to use on the stack machine? Obviously, the alphabet for the strings has to be the same as the string alphabet over here. That is to say, the terminal alphabet, which would be A's and B's. So in this column, you're going to see just A's and B's, and possibly epsilons also. In the pop and push columns is these things will be strings in the stack alphabet. And when you're doing this, the stack alphabet in this example is A, B, S, and T. So what you might see appearing on the stack is any combination of any of these letters that are used in the grammar. So on the stack could appear, little A's and B's. Also could appear S and T's. All right, here's how you do it. Like I said, the procedure is very simple, although kind of mysterious about why exactly it works. We need to do some examples, I think, to convince you that it really works. But let me just tell you how to do it first of all. Every grammar production becomes an epsilon transition in the stack machine, and they work like this. When I see S goes to A, B, S, A, the transition looks like epsilon S A, B, S, A. So this is very easy to remember how to do it. Let me just write that in words. Each grammar production production. I wrote grammar with one M. Each grammar production, if it looks something like, you know, X goes to Z, this makes a stack. Come on now. This makes a stack rule that looks like epsilon X Z. So every one of these productions, there are 4 of them, makes an epsilon transition. You know, we consider these as 4 separate things, but separated by these bars. So the next one is S goes to T. That looks like epsilon S T. There you go. Next one, T goes to BT. Looks like epsilon T BT. Simple enough. And then finally, T goes to epsilon. You do that one too. Epsilon T epsilon. All right. This is not the whole stack machine. You actually need a few more, but the few more ones are always of exactly the same form. You always look like A epsilon, B epsilon. And this is the whole stack machine. So these 4 here, they come from the grammar productions. These 4, so they're sort of one type. They come from the grammar productions, as I described right there. And then these last 2 are always special ones. And every time you do this, it always looks exactly the same. Each non-terminal gets a rule, you know, that looks like X epsilon. You always do it in exactly that way. It turns out, if you followed these instructions, this stack machine, it produces the same strings as the grammar. And I thought, just to convince you of that, let's try and do that same derivation of that string that I did a moment ago. I hope you can still see it on your paper. I want to do that same derivation, but do it on the stack machine and verify that that string is accepted on this stack machine. Let's do it over here. So I hope you still see that string on your paper. Here is what it is. I'm going to start off A, B, A, B, 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 A. You know, on the stack, we started up this way, right? Comma, S. And we have to do these rules here, one after each other, and end up with epsilon, comma, epsilon. That's what it means to be accepted on the stack machine. All right, let's see if we can do it. Your strategy is look at the grammar derivation that you just did a moment ago and do those same steps here. So at the grammar derivation, the first production that we did in the grammar derivation was S goes to ABSA. So I'm going to do the corresponding rule in the stack machine is this one, which came from that rule S goes to ABSA. So I'm going to do this one first. It is an epsilon transition. So we're not going to change the input string. A, B, A, B, 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 A, comma. We are going to change this. We pop the S, so this gets thrown away entirely and replaced by that. All right. A, B, S, A. Okay? This was copying the grammar step that we did at the beginning of the grammar derivation. All right, and now the next step, you don't immediately do the next step in the grammar derivation. We are now going to do these 2 rules here to clear off the front of the stack until the non-terminal is on the front of the stack again. So here we have AB at the beginning of the input string, and we also have AB here. So I'm going to do this rule, read A, pop A, push epsilon. That basically cancels, it erases this A because I read this A, and it throws away this one because it got popped. So that is going to look like B, A, B, 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 A, comma, B, S, A, right? I did this line here. You read A, so this A went away, and you popped this A, so that A went away, and I replaced it by epsilon, so nothing new appears. All right, and then I do this line to clear the B here and the B here. The idea is you do one grammar step, and then you got to kind of sweep away the garbage that got produced at the beginning of each of the strings over here, and you use the epsilons to do that. So now I am going to use the B transition here, right? Read B, pop B, push epsilon. Okay, so this B gets read, so that goes away, and then this B gets popped, so that goes away. All right, there we go. And now we are ready to continue with the next grammar derivation. See, it's not possible to do one of these guys anymore because we don't, because we have S on the top of the stack. So actually, we have to do one of these two rules. And for guidance, you know, which one of these two rules should we do? Look back at your grammar derivation. We only did the first step of that grammar derivation, and then we did this kind of cleanup operations to clear out the A's and B's. Do the next step in that grammar derivation, which was the second step we did was, again, S goes to A, B, S, A. And that's the step I'm going to do here. So I'm going to do this first line here. It's a epsilon transition, so I'm not going to change the input string. A, B, 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 A. And then this S gets popped and replaced by A, B, S, A. So it becomes A, B, S, A, right? This original S got popped away. And it was replaced by ABSA, and then I still have this A on the end because that's this A, which is still on the bottom of the stack. All right, now I have A and B on the top of the stack. I am going to use these two A-B transitions here to throw those away, reading the first A. So I read this A, doing this line here, read this A, pop this A. Everything else stays the same. B, 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 A, B, S, A. All right, and then I do this for the B to clear this B and this B. All right, B, 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 A, comma, S, A. All right. This is how we do it. You follow the grammar steps, and after each grammar step, you use these two last rules to clear out the extra stuff. And hopefully, eventually, if it all works out, we will, at the very end, clear everything out, and it'll be epsilon, comma, epsilon, which is what we're looking for. All right. What should we do next? The next step that we did in the grammar, if you look back, was change S to a T in the grammar. So I'm going to do this line, which is the stack line that corresponds to that grammar production. So this is an epsilon, so it does not change the input string. B, 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 A. S, we pop the S and replace it with a T. So it's now TAA. Okay? Ordinarily, I would like clear out non-terminals on the front of each here, but there aren't any. So we go immediately to the next grammar production step, which shall be what do we do next? We did T goes to BT. All right, so I'm going to do that. T goes to BT. That would be this line here. Read epsilon, so the input string stays the same. Pop T, push BT. So this T we pop and replace with a BT. Yeah, right? Okay, now we can clear a B on the front of each. So I do this line there with the B's. I read this B. What remains is BBAA. I pop this B. What remains over here is TAA. All right. You get the idea? I hope so. Let's continue. The next grammar step that we did was T goes to BT. Again, I'm going to do that line, which is right here. Pop T, push BT. So we get B, B, A. This is an epsilon transition, so there's no change to the input string. This T is replaced with BT. All right, I'm running out of room here. I'm going to have to start again at the top. I hope you don't mind. Don't try that at home. All right, let's continue. I'm going to clear out these B's on the front by doing this rule here. Read B, pop B, push epsilon. I read the first B. I got BAA. I pop this B. I got TAA. All right. One more time, we're going to do this rule. T goes to BT in the grammar, which is on the stack machine. Read epsilon, pop T, push BT. So I go read epsilon. That means my input string stays the same. Pop T, push BT. This T turns into a BT, AA. All right, now I clear out the B's on the front by this last rule here. I got AA, comma, TAA. Okay, we're almost done here. The last grammar production that we did was at the very end, we did T goes to epsilon. That corresponds to this rule on the stack machine, so let's do it. It's an epsilon, which means I do not change the input string, and then pop T, push epsilon. This T goes away, and nothing replaces it. Now I have AAAA. Now I want to get epsilon, comma, epsilon, and I can just do this rule 2 times. It will read each A, pop each A off the stack. So do it once, I get A, comma A. Do it one more time, I get epsilon, comma epsilon. Hooray! This is accepted. All right? Do you see the procedure? The procedure involves, first of all, if you want to see if a word, show that a word is accepted on the stack machine, first of all, write down a grammar derivation. And then copy the grammar derivation steps one at a time. And hopefully it'll all work out and you'll get down to epsilon, comma epsilon. I got one for you to try. Can you try it? Can I trust you to pause your video and try to do one on your own? See if you can on the stack machine. How about show A, B, 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 A is accepted. Like this, right? I want you to start A, B, 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 A, and eventually comma S, right? And then eventually do these guys, get down to epsilon, comma epsilon. And my advice to you is, first, try to derive this using the grammar. That's easier, in my opinion, than looking at these and trying to figure out which steps to do in order. So first, write down a grammar derivation of that, and then try and copy your grammar derivation of this step by step, and you know, clear out the extra letters as you go, and see if you can get down to epsilon, comma epsilon. Go for it. I know you can do it. Alright, here's how I did it. First, I'm going to follow my own advice. First, do it on the grammar. I want to make the string A, B, 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 A. Just write that. A, B, 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 A, right? So, I'm going to start with S. I'll go S goes to A, B, S, A, because I need a A, B at the beginning. Next, I want to see a new B without an A, so I have to go S goes to T, A, B, T, A. Then I have to go T goes to B, T, so A, B, B, T, A. Do that again. Come on now. A, B, 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 T, A, and then finally T goes to epsilon. No, I need another B. All right. A, B, 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 T, A, and now finally T goes to epsilon, and it's done. A, B, 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 A. Right? Okay, so this is the grammar derivation. I'm going to try to copy these steps and make a stack machine derivation, which shows that that string is accepted. So I go A, B, 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 A, comma, S. Right? And what did I do first in the grammar was S goes to A, B, S, A. So I'm going to do the first rule in the stack machine, which was epsilon, S, A, B, S, A. So it's an epsilon, so I don't change the input string. A, B, 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 A, B, S, A. All right? Yeah, that's the right arrow. Okay, and now I'm going to clear out the A and the B on the front of each of these. All right? I do the AA epsilon, clears the first A, so it's A. I just wrote it again. The AB epsilon clears the first A, so it's B, 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 A, comma. And it clears this A also, B, S, A. Right? Now I can clear these B's also by doing the BB epsilon rule. So now it's going to say BBBA, comma, SA. All right? Now I've done all the clearing that I can do. We got to do the next step in the grammar derivation, which was S goes to T. So here I'm going to do the stack rule, epsilon S T. All right? Let's do it. Epsilon S T. So it's going to say B, 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 A, T, A now. All right, then I'm going to do T goes to BT because I want to clear some B's. T goes to BT. Looks like B, 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 A, B, T, A. And now I clear a B here. B, B, A, T, A. Right? I have more B's to clear, so I do another. B goes to TB. B, B, A, B, T, A. Right? Now I clear a B. B, A, T, A. All right, I have one final B to clear. I do another. B goes to TB. B goes to TB. All right, BA, comma, BTA. Okay, clear this B here and here. A, comma, TA. I don't want this T anymore. I go T goes to epsilon. A, go, comma, A. And then finally, clear those A's. Epsilon, epsilon. There you go. I hope you said something like this. Generally speaking, if you have a grammar derivation of some string, the stack computation is going to be longer than the grammar one, right? You can tell because you have to match each grammar step corresponds to one step down here, but then in between you have to do a bunch of clearing operations to clear out the extra letters. But anyway, that's how you do it, and it's pretty straightforward. You know, once you get the hang of it, it's not hard to do. You just got to remember how to do it. This procedure works in general for any context-free grammar. It needs to be context-free, but it does work in general for any context-free grammar. Here's just another quick example. Translating the grammar into the machine. How about one of our favorites? How about S goes to A, S, B, or epsilon? Remember, this is the grammar for the language A to the N, B to the N. I'm going to try one of my other Marcus. This is the language for A to the N, B to the N. Let's translate this into a stack machine. You know, I'll do my, ooh, that looks pretty good. Read, pop, push. All right. Remember, every grammar production gives you an epsilon transition here. So it's going to be read, epsilon, pop S, push A, S, B. That's the first one. And then I also have S goes to epsilon, which will look like read, epsilon, pop S, push epsilon. So these are the two rules given by the grammar productions. We also need the special rules for the clearing out of the letters. A, epsilon, B, B, epsilon. And that's it. This is the stack machine, which does this same language right there. There's not a lot to it. How about this one? I got one for you all to try again. Oh, squeak. How about you try make a stack machine? This is easy if you know the procedure. Make a stack machine for this grammar, this context-free grammar. S goes to ASC or AS or BS or epsilon. This is not a little s. There's no little s. Come on now. BS like that. All right. And show how A, B, A, C, C is accepted by the stack machine. All right, see if you can do it. It's me from the future. I meant to say show that A, B, I've got to get it right this time. A, C, C is accepted. I think I left out an A there. That's what I meant. Sorry about that. Go to it. Did you do it? I hope you did it. I hope you weren't just waiting for me to do it. How do you do it? It's not hard, really. You just got to know the procedure and do the procedure. So we begin by writing the stack rules for this. Read, pop, push. What do we get? S goes to ASC. Gives me epsilon, S, ASC. What? Big C, little s? No. We don't write little s's in this class. Not in this house. Could I just say for a moment, why is it that this only works for context-free grammars? I said before, it's not possible to translate any old grammar. You can't just take any grammar and turn it into a stack machine. It must be context-free. And remember, what context-free means is in every grammar production, the left side must be just a single non-terminal. And the reason that's necessary is because the left side of the production is what ends up in this column, the pop column, And on a stack machine, you are only allowed to pop one letter at a time. This is the only reason why. This only works for context-free grammar. If your grammar is not context-free, that means the left side of the production might not be just a single letter, and then this will get screwed up. So this is why it must be context-free. All right, read, pop, push. That was the first one. Then I also have S goes to AS, so that's going to be epsilon S AS. Then I have S goes to BS, which is going to be epsilon S BS. Then I have S goes to epsilon, which is going to be epsilon S epsilon. And then, as always, we have the sort of clear out ones. I go A epsilon, also B epsilon, and also C epsilon. In this case, we have A, B, and C. All right. This is your stack machine. I hope that's the same machine as you got. So I said make a stack machine and show how this string ABACC is accepted by the stack machine. Let's try and do that. ABAACC. Oh, my kid's drumming again. Can you hear that? Okay, how do we accept ABAACC? We are going to first derive this using the grammar. So I go S goes to... I gotta tell my kid to stop drumming. Sorry. Should I yell? Stop the drumming! I think she heard me. We'll see. I go... Alright, to get this on the grammar, ABAACC, you may have to think about this a little bit. How do I get that using the grammar rules? I think first I should go S goes to ASC. That gives me the first A and the last C. And then next I want to see a B, so maybe I'll go S goes to BS. S goes to BS, so A, B, S, C. And now I'll go S goes to A, S, A, B, A, S, C. And then I'm going to do S goes to ASC again. A, B, A, S, C, C. And now S goes to epsilon, and we're done. A, B, A, C, C. All right? That's how we do it. What about on the stack machine? Let's try it. So I'm going to try and squeeze this in here. I hope this is enough space. I go A, B, A, C, C, comma, S. All right, and I do my stack moves. So the first grammar move was S goes to ASC, so I do my stack move A, B, A, C, C, A, S, C. Now I clear this A, B, A, C, C, S, C. All right, the next grammar step was S goes to BS, so I do that. B, A, C, C, B, S, C. And now I clear these B's. I get A, C, C, S, C. All right, now the next grammar step I did was S goes to AS, so I'm going to do that. A, C, C, S goes to AS, makes this ASC. Clear these A's on the front. I get A, C, C, S, C. All right, next grammar step I did was S goes to ASC, so do that. A, C, C, A, S, C, C. Clear the A's on the front. C, C, S, C, C. And then finally I did S goes to epsilon. So I go C, 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 C like that. S became epsilon. And then these, each of them clear off one at a time. I hope that's what you got. This is how we do it. If that made sense to you, then you should feel great about that. All right, I think that's it.